Thanks for joining. Yeah, I'm Daniel, working for Portworx, as already said. I think I'm standing between you and the lunch break, so I will hurry up. And yeah, I will talk about PVCs, persistent storage in Kubernetes, because we see often in customer environments that this is a thing which comes to customer minds when they are on their Kubernetes journey. And let's start high level. I will dig deeper into the details, how it works, how it looks like. But first, high level, we see when we come to customers, discuss about Portworx, discuss about Kubernetes, we see there is an agenda for application modernization. So people want to move and migrate workloads from existing environments into Kubernetes. And there are IT managers who read in the CIO magazine, Kubernetes is the next big thing. So we need to do this. We start with it. And we want to have all applications over a defined amount of time on the Kubernetes platform. It's so easy, just do it, which is not the reality. So the reality looks a little bit different. And we typically see three phases in customers when they are on the Kubernetes journey. And the first phase is they start with stateless applications. And stateless, in our terms, means there is no data stored within the cluster. So your applications run on the Kubernetes cluster. They get their data from somewhere, calculate this data, and throw it to somewhere else. And somewhere is not inside the Kubernetes cluster. When people adopted this and managing Kubernetes, running Kubernetes, defined all their processes and things, they then start also deploying persistent workloads on their clusters, because every Kubernetes platform brings something with it which can provide persistent storage. For example, if you're running an on-premise cluster on vSphere, there's CSI providers for vSphere. If you're running in the public cloud, EKS, Google, Azure, what else, there's always a way how to deal with persistent storage. And this is typically in phase number 2. So people start deploying non-critical stateful workloads on their Kubernetes clusters. Most cases, it's the developer developing a microservice and deploying a Postgres database or a MongoDB or stuff like this on their clusters. And at this point, people gather experience how this works, how CSI in general works. If they're running on-premise, they might also integrate storage arrays into these platforms and find out how this works or not works. And this is an interesting phase. And it gets interesting in the third phase, because if this works well, people tend to put critical workloads on this. So business-critical workloads, business-critical data on their Kubernetes clusters. And at this point, they start rethinking about this storage in Kubernetes, because now they get questions about how is this data secured? How do we encrypt this data? Because it's now our business-critical data. How can we migrate this data away from one Kubernetes cluster into another, or away from one cloud vendor to another cloud vendor? Or how can we do HA between cloud regions? And this all gets complicated when you have persistent state in your Kubernetes clusters, because just deploying an application on another cluster is an easy thing. It's all YAML specs in a GitHub repository, easy. But when you want to migrate the state from one vendor to another, from one Kubernetes platform to another, this can get complicated, and you need to develop processes and tools how to do this. And with Portworx, we can help you with this. So what does Portworx actually do before digging deeper into how you can do this stuff? Portworx is an abstraction layer for storage in Kubernetes. Portworx runs in each and every Kubernetes distribution, and it also runs on each and every Kubernetes infrastructure. You always have one Portworx instance running in one Kubernetes cluster, and it's deployed using an operator, so it's all Kubernetes native. And when you deploy it inside the cluster, you can configure it with YAML specs. So this also integrates very well with automated pipelines and stuff like this. And Portworx itself runs inside the Kubernetes cluster. And the basic design principle is we take the block storage from the platform you're running on and integrate a virtualization layer. So we consume block storage from the Kubernetes worker nodes of your platform and put this into an abstraction layer. And out of this abstraction layer, we do all the storage magic I will dig deeper into later. But again, the basic design principle is unused block storage from the worker nodes gets into an abstraction layer, into a pool, we call it. And out of this pool, you then can create the persistent volume claims using storage classes, as you might know. So these volumes we can create can be read-write once or read-write many volumes. This is just integrated into the product. Now, when talking about using unused block storage from the Kubernetes worker nodes, depending on the platform you're running, this could be technically mean different things. Because if your Kubernetes cluster, for example, runs on vSphere, usually unused block storage on a worker node means it's a VMDK being attached to a VM. If you're running Amazon EKS, it's an EBS volume being attached to an EC2 instance. Same applies to Google, to Azure, or if you're running bare metal, it's a disk or a LAN being attached to the bare metal server. So when running your Kubernetes cluster on virtualized environments, we have another layer we call orchestration layer, which enables you to automate this deployment of the backend storage, of the unused block storage to the worker node. So for example, if you're running on vSphere, you can tell Portworx in the YAML configuration spec, hey, you're running on a vSphere cluster, this is the vCenter server, and I want to have each and every Kubernetes worker node providing 100 gigabytes to the storage pool. So if you have a 10-node cluster, Portworx would start up, would connect to the vCenter, and would deploy 100 gig VMDK out of a data store to the VM worker node. And if your cluster is up and running, so roughly around 8 or 10 minutes, you would have 1 terabyte of storage in your storage pool for Portworx. Same applies to AWS, or to Google, or to Azure, to IBM Cloud, to Oracle Cloud. So in each of these clouds, in each of these automated environments, we can provision the backend storage we need by ourselves. If your Kubernetes cluster runs on an environment we don't support with the orchestration layer, it's on you to provide unused block storage to the Kubernetes worker nodes. As I said, on a bare metal cluster, you plug in disks, SSDs, or LANs to the worker nodes. So this is the basic idea of how we provide storage into our pool and how we create this abstraction layer. And on top of this abstraction layer, we can do now many interesting things which might be not possible with the built-in capabilities of the platform you're running. So with Portworx, you can now create multiple storage classes. Well, that's boring because you can do this everywhere. But we can provide block and file storage to your workloads. We can also provide multiple performance classes to your workloads. So this means whenever a worker node provides backend storage to the pool, we benchmark this backend storage and we classify it if it's slow, medium, or fast storage. And within your storage classes, you can now reference and say, okay, I need SSD class storage, so fast storage, or I need slow storage. So you could have multiple classes of storage within the cluster and you just consume it using the storage classes. And we'll also offer multiple layers of protection within the cluster, because when I say we use unused block storage from worker nodes, what actually happens if you lose a worker node? You would lose the data which is attached to this worker node. So we have a protection level, which means we create redundancy within the cluster. And you can lose a worker node, you can lose an availability zone within your cluster without losing your actual data. So this is about high availability within the same cluster. Now, when we take a look into the applications, we are always application consistent, application granular. And this is very interesting when it comes to snapshots. Many CSI implementations can do snapshots. This is nothing new because it's a basic principle of the CSI definition. But many implementations differ. So if you want to do a snapshot of your application, it might be a difference if you're using the Amazon EBS CSI driver or the vSphere CSI driver, because there might be some annotations doing some special things which the vendor of your choice can offer. And this could end up in, when you have multiple clusters on multiple platforms, you need to define multiple ways of how to snapshot persistent data, because the annotations differ. You could have one annotation on AWS which you cannot use on vSphere and vice versa. With Portworx, it's always the same. When you run Portworx, it doesn't matter any longer for the consumer of your storage what's the underlying infrastructure. So if you figure out how to do a snapshot with the Portworx environment for your application, it will work on each and every Portworx instance, no matter if it's AWS, Azure, bare metal, what else. And we also don't care about the underlying infrastructure or the underlying Kubernetes distribution. So we run on OpenShift, Rancher, your choice. So when doing snapshots of an application, it's important to know for your storage vendor that applications within Kubernetes can run in multiple replicas, consuming multiple volumes. So to make a useful snapshot, for example, of a Postgres database running in a namespace of Kubernetes, it's important to tell Postgres that it will be actually be snapshotted, then taking the snapshot of all volumes at the same time, and then maybe also tell the Postgres application that it now can continue doing its stuff. And this is all integrated, and this is all Kubernetes native within Portworx. So you define YAML specs, and you can apply these YAML specs in each and every of your clusters. So we can do application consistent snapshots within the cluster of your persistent applications. Same applies to encryption. Well, obviously today you can encrypt on every place in your IT stack. For example, if you're running on-premise, a storage system can encrypt data. But the problem is, if you're responsible for the Kubernetes platform, if you're the site reliability engineer, and it's your task to ensure that data is encrypted, you could either try and find out where in your IT stack encryption will be applied to your data, or you can run Portworx. With Portworx, encryption is done at this point where the data gets stored on the block storage of the worker nodes. So if you configure encryption within Portworx, it works the same no matter which infrastructure you're running. Portworx encrypts the data, and all data at rest will be encrypted, independent from what your platform actually could do or could not do, or where it could encrypt or where it could not encrypt. And this helps you also to get compliance over your clusters. And this is really important if you're running hybrid cloud environments or having multiple public cloud vendors supplying your Kubernetes clusters. And last but not least, at this point, it's about replication. So now with having this abstraction layer of Portworx in your cluster, we are now able to replicate data between different Kubernetes environments. And this is being used for disaster recovery. So you could think about having an on-premise Kubernetes cluster running on VMware Tanzu and replicating namespaces out of this Tanzu cluster into a public cloud Amazon EKS instance. So with Portworx, you can replicate the full namespace from one cluster to another. And well, this is boring when it comes to the application deployments because that's YAML specs out of GitOps repository, easy thing. But it gets difficult when it comes to the persistent volumes because Portworx actually migrates these volumes from one cluster to another. So our customers are using this to implement synchronous or asynchronous replications between Kubernetes clusters. This is something storage people know. So migrating or copying data from one data center to another is nothing new in the classical IT world. But now we can do this Kubernetes native and on a Kubernetes level. And I will dig deeper into this, how this looks like, how this is configured later at this presentation. But there's no limit. So, for example, asynchronous replication works independent from underlying infrastructures, independent from underlying clouds, independent from underlying Kubernetes distributions. So as long as Portworx runs in this cluster, it can replicate the data to another Portworx cluster. And we use the same technology to also enable migration. So having the capability of snapshotting a namespace and all its volumes and replicating it to another cluster is being used to migrate. So we have customers who did their OpenShift 3 to OpenShift 4 migrations with Portworx. So they actually just migrated their namespaces out of the old cluster and then deleted it. Or we also have customers who are doing their testing of applications with Portworx. So for example, if you have a running application, it's a classical 3-tier, let's say it this way. You have the application, you have a middleware, you have some databases, or you have just the application in the database, and something strange happens, and you don't exactly know, is it the application, is it the database, is it the data inside the database? So your developers need a full copy of the stack. Then with Portworx, you just migrate or copy this namespace to your testing clusters, and then you can do the troubleshooting. So this is being used to migrate or to upgrade all this stuff. And again, there's no limit for the underlying clouds, for the underlying infrastructures, all these pieces. And I want to dig deeper into this, how this looks like on the next slide. So this is just an example slide, again, high level. I have one Kubernetes cluster which is running, for example, on premises. There are 3 namespaces, so Postgres, Mongo, and MySQL is running inside there. And Portworx is providing the persistent volume claims for these workloads. Now you can set up a second cluster, which could be Amazon EKS or Google GKE, no matter what, so independent, also with Portworx. And now you can create a so-called cluster pair. I will dig deeper into the details of this at the next slide. And you also need an object store in between. We need to sync this. And now Portworx would create these cluster pairs. So there's a link now between these two clusters. And now you can create a migration. And the migration defines what to migrate. And Portworx would now start following a schedule, migrating these namespaces to the other cluster. For the DR case, it would just do every, for example, 5 minutes, replicate the namespace from the source to the destination. And if you want, you can do this application consistent. So it would take a snapshot of the source namespace, would replicate this to the destination cluster, and would also create all the Kubernetes elements in the destination cluster. So if you now would, at this point, take a look into the second cluster, do a kubectl get PVC, get all PVC, you would see all the PVCs, you would see all the services, all the deployments, all the ingress definitions in the second cluster. The only difference we do by default is we don't start the application. So we scale the replicas down to 0, because in a DR scenario, you don't want the application to run at the second side without actually having a disaster on the first side. And in case of a disaster, you would have a single command in the second cluster, which is a Portworx command, which says, hey, Portworx, there was a disaster. Scale up all replicas to the original number you know from the source. We store this number inside an annotation and read it out and scale them up. So this happens automatically in the background. You just hit this single command and say, there's a disaster, start. And then the Kubernetes cluster would just pull the images, start the containers, and your application will actually run. We can do the same also as a sync migration, so not following a schedule, but ensuring that every bit which is written on the left side gets transferred to the right side before it's getting back committed to the writer. But this is another architecture. So now, when going into the details of this, I just mentioned it. So prerequisites, what do you need for? Well, Portworx Enterprise must be up and running on both sides, so you need to install it on both sides. You need to expose the Kubernetes API and the Portworx API on the target cluster, because the source cluster needs to be able to connect to this cluster. This is network layer 7, so nothing special. And you need an object store. Why do you need it? For the sync of the data, we need the object store. So we don't transfer the data directly from the source to the destination. We transfer it into an object store, and the destination cluster pulls the data out of this object store. So this can be S3 compatible. So if you're running in the public cloud, you just need an S3 bucket. If you do this on-premise, you can use MinIO or a hardware providing object storage. There's one more component. It's called Stork. It's an open source component we are using. We are also developing. And Stork is managing all these snapshots on migrations within Portworx. So it's the storage orchestration runtime for Kubernetes. This piece of our software, which is a part of our default deployment, is managing all things related to snapshots, to migration, and all this stuff. So this is our orchestrator. And yeah, this is open source, so you can take a look into it, what it can do. Basically, all the pieces I'm showing here are being managed by this. It's, yeah, as I said, part of the default Portworx setup. And it provides a custom resource definition within your cluster, which makes this migration process easily configurable. So it's basically 3 simple steps you need to do to enable migrations between these two Portworx clusters. And I just want to dig deeper into what to do. So first of all, you need to create the so-called cluster pair. A cluster pair means always there's a source cluster and there's a destination cluster. You can have multiple cluster pairs in your environment. So if you have multiple Kubernetes clusters, you can build multiple connections between those clusters. And the cluster pair, there's one command you need to run, which looks very long, but it's basically quite easy. So you just tell Stork to create the cluster pair, you give it a name, you give it the kubeconfig files of the source and the destination cluster, and you give it the secrets for the S3 bucket it needs to synchronize the data. And after you created this, the CRD will be created in your cluster, Here, if you run this command, it will create 2 cluster pairs. So one in cluster 1 having this as a source and the other as destination. It will also automatically create on the other cluster a second cluster pair, which defines the second cluster as source and the first one as destination. And this is because if you do a failover, you might also later want to do a failback. And then it's useful to have it defined on both ways. So this creates actually the cluster pair. You can check, so you can check this CRD if it's actually there, how it looks like, and you get out an output of this CRD. And the important pieces are the last 2: scheduler status ready, storage status ready. This means everything has been set up. Both clusters can see each other. Everything should be able to run. So this is all just Kubernetes stuff. Second, you need to create a policy. And this is only needed if you want to do async DR. For migration, you don't need it because, well, migration is a one-time process. DR means you do multiple, or this will be repeated every X amount of time. So the schedule policy, again, is a CRD, which just defines how often things happen. You could create multiple of those schedule policies because they will be later referenced in the actual configuration. So here we create a schedule policy. We call it a 5-minute sync, and it will happen every 5 minutes. There's also possibility of defining times, time of date, month, week, everything. That's basically how it looks like. And the third thing you need to do to set this up is you create the actual migration schedule. And that's the most important point. So this is a CRD defining which namespaces are being transferred from source to destination. So this here says it's named migrate Postgres. It's placed in the kube system namespace. And now you create a spec which says, I want to reference cluster pair 1. You remember, this is the first we define. So defining cluster 1 is talking to cluster 2. Here you could also reference other cluster pairs. Secondly, it says include resources. This means, should we copy the Kubernetes resources? This can make sense or cannot make sense. I will show in the next slide. So here you can check if you want to just migrate all Kubernetes resources, deployment, services, ingress, all this stuff. The next one is start applications. This is here set to false. This means should the application which has been migrated to the destination, should it be started there or should it be just be there as a shadow? So for DR, you might use the false setting. And the last thing here is include volumes. This means should Portworx migrate the volumes? I don't know a use case why you should not, because that's the sense of Portworx, but you can disable it if you want. And then you can choose the namespaces. So you can say, OK, I want to have the Postgres namespace being migrated. Or the other option would be you label your namespaces. This is more the self-service way. And you can say, OK, take all namespaces which have the label migrate equals 5 minutes. So you can transfer this into a self-service for your users. If your users label the namespace with this tag, then this namespace will be migrated from Portworx. If they don't label it, it won't be. And yeah, last settings, which schedule policy should we use? So every 5 minutes, suspend and auto-suspend, these settings are important. If you have a source and a destination and you replicate data from the source to the destination, what should Portworx do if it detects that the destination cluster goes up? So the failure happened. You might have lost your first cluster, but maybe it comes back because it's a networking issue. So you enable the disaster recovery procedure on the second cluster. And what could now happen if the source cluster comes back and tries to push data into the now running production cluster? This might have bad results for your data. So we have a setting called auto-suspend, which means as soon as the source cluster detects that the destination cluster is up, and the data there is newer, it won't do anything. This is just for protecting your data. So this is the migration schedule. Quite easy thing. You apply it to your namespace, and then it will run, and you can also check it. So first command shows you which migration schedules have been created. The second command just shows you which migrations have been started. So as I said, we do migration every 5 minutes. And with the second commands, you would just see which migrations have been done and what's the result of them. So there you would also see if it fails or doesn't work. So this is the 3 steps you need. But there's another question. I said we don't care about what's the Kubernetes distribution on your source and your destination, or what's the platform on your source and your destination. So what happens actually when these clusters differ? A good example is OpenShift. If your source cluster is an OpenShift cluster and you have OpenShift routes defined, and you do a DR to an Amazon EKS cluster, Well, EKS doesn't know anything about routes. Doesn't make sense to replicate routes to this cluster. So what's the strategy to solve these issues? And there are others. So last year I did a demo here between an Amazon or a Google cluster, which was the source, and an Amazon cluster, which was the destination. If you ever worked with the Amazon clusters, ingress is not an easy thing. So it's not just there. You need to configure it. On Google, it's just there. So if you configure a configuration like this, it might not make sense to have the ingress being migrated to the Amazon instance because it cannot use it. So what happens if source and destination differ and you need different settings? There's different strategies you can follow. So first of all, you can set not to migrate Kubernetes resources at all. This was the setting I've shown, migrate resources true or false, and deploy all Kubernetes resources from your Git repository. So create another branch for the destination cluster, and there you set all the settings you need for this destination cluster. For example, coming back to my example, you're migrating from OpenShift to EKS. You create another branch in your repository, which creates all the Kubernetes objects on the EKS cluster without routes and the correct ingress definitions. Second thing you could do, so this is the actual setting, you've seen it in the other slide. The second thing you could do with Portworx is you can tell Portworx only to migrate labeled resources. So you can label all your Kubernetes resources if you want, if they need to be migrated or not. So the user could choose by himself if they want to migrate or not. So this means you can, in the migration definition, you can define selectors, meaning here, for example, px migrate equals true. Or you can also exclude labeled resources. So if you want to say, okay, OpenShift routes doesn't matter on Amazon, then you could label all these route objects within your cluster with a label called no migrate equals true, and put this into the exclude selectors section. So you could include or exclude things for the migration. And the last thing you could do, which is also quite interesting, you could do a resource transformation. So this is also a function of Portworx, meaning if your clusters don't differ that much, but you need to change an annotation or you need to change a label for the destination cluster, you can do a resource transformation. And this looks like this. So with resource transformation, you can add or modify or delete resources while they are being transferred from the source to the destination. And it looks like this. So the resource definition, again, it's a CRD we create. And here you can say, okay, the transform spec for this resource transformation for my Postgres namespace is we take the spec type load balancer, or we change the spec service type load to load balancer. So this is the destination, how it should look like. So whenever it finds a service definition, which could be node IP or cluster, no, not cluster, load balancer, it will change it to load balancer. So node IP will be changed to load balancer. That's the correct way. Or it can also change labels within this service. So it modifies these labels, these key pairs to handler equals project, application equals Postgres 2. So with this resource transformation, you can change objects in flight. So when they're being migrated from source to destination. And this, ends my presentation. So if you have, I'm good on time.
Yeah.
If you have any questions, feel free to ask.
Excellent presentation. I really liked learning more about Portworx, which is something that I didn't know about. So we have some questions on Slido. The first one is, how are encryption keys stored?
Yeah, so anonymous people are interested where we store our encryption keys. That's good. The encryption keys can be stored in the Kubernetes secrets. Well, this might not be the best way to do it. So we integrate with key management systems. So if you're running on-premise, you can use HashiCorp Vault. If you're running in the supported public clouds, we support these key management systems from the public cloud vendors. So you don't need to store them in the Kubernetes secrets.
It's good that the ContainerDays audience is interested in security.
That's good. Yeah, that's one of the key use cases we see in many customers.
This is, I think, a bit more of a specific question, but if I have a storage class configured to use a block storage not located on worker nodes but somewhere externally, can Portworx work with that as well?
There's my favorite answer. It depends. You need to attach this block storage to your worker nodes. So you can do this by yourself. For example, if this is an iSCSI block storage, you can just go to your worker nodes and attach these volumes or the LUNs of this iSCSI block storage to these worker nodes. This would be a manual step, but you can do this. And you can also automate this. Same applies to fiber channels. So if you have bare metal nodes, you can just provide these LUNs to the worker nodes. And then you can tell Portworx, hey, by the way, you are not running in any cloud. Take every storage or every block storage you find on the worker node, and then it would take every block storage it finds on the worker node. Or you can be more granular, so you can do this heavily complicated if you want. You can create groups of nodes following labels and selectors, as you always do in Kubernetes, and can tell, okay, on this group of nodes, I want to have Portworx using dev SDD or dev SDE or some other objects or volumes. So, but back to the question, the key is you need to attach this block storage to your worker nodes. There's one exception, and this is storage from Pure Storage. So we can automate the attachment of Pure Storage to the cluster. But all other vendors, we support them. It will work, but you need to attach them manually or run an automation for this.
Love the "it depends" answer. Does the DR require the fallback cluster to always stay up, or is it possible to only keep control plane up to save cost?
That's a good question. So I think the fallback cluster means the second cluster where we replicate to. So the second cluster, we need at least 3 worker nodes in the second cluster and a sufficient amount of storage from the backend to store all your data. So it's not sufficient to just have the control plane. But what customers do is, for example, if they have a large source cluster, hundreds of worker nodes running the source, and they use Portworx to set up an asynchronous copy, then the destination cluster can be much smaller. So it needs to be at least 3 worker nodes. But that's enough. So Portworx will run on this cluster and will replicate the data to this cluster and provide backend storage and do all this stuff. And just in case of a disaster, you need to create your runbook to scale this cluster up. So the destination or the fallback cluster doesn't need to have the same size of the source cluster, but it needs to be there. So just the control plane is not enough. You need at least 3 worker nodes.
Cool. The next question is about how much of what you've shown today is available as open source.
Yeah, well, the Stork is open source, our operator is open source, but the rest is a commercial offering.
Cool. And the last question, I think that's all we have time for, is, I thought this was quite interesting. Does Portworx need to be installed from the beginning, or can it be installed to an existing cluster?
Yeah, you can install Portworx into your Kubernetes cluster whenever you like. So we can also run in parallel to other CSI provisioners. We have many customers running their clusters with traditional CSI providers. So you can just install Portworx as you do with every other Kubernetes application. So this is just... yeah, Portworx is just a Kubernetes application, so you install it on your cluster at any point you want. The only issue is if you already have provisioned PVCs using other CSI provisioners, then there's no simple click way to migrate these volumes to Portworx. We have a tool for this, so you can do this, but it's not that we just take the volumes you already have and own it and do all the Portworx magic with them now. But you can install it whenever you want.
Now, I said that, oh no, sorry. Anyways, there was a question about...
Yeah, was another question, yeah.
Sorry, let me find it.
I told her to skip this because I don't want to answer. No, I think the question was about when the second cluster, I just read it, when the second cluster has newer data than the source cluster.
There we go.
What if the second cluster have newer data when the first cluster... Then the first cluster came online.
So the second cluster has newer data, and then the first cluster comes online.
Yep.
And how do you sync that?
Yeah. So first of all, we have this function of auto-suspend. So if you have the auto-suspend enabled, the first cluster would not try to override the newer data on the second cluster. It would just detect it has been walked forward, and I don't do anything. Then we have a process where you can just do a failback if you want. So if the second cluster is now productive and you don't want to have this productive forever, you want to fail back to the first cluster, our documentation states how to do this. So basically, technically, you disable the synchronization from the old source to the destination. You just disable it, tell Portworx, don't do this any longer, and then you replicate the data back. So this is a process which is described in the documentation. So that's nothing fancy.
Thank you so much, Daniel. You answered so many questions as well. Remember to go past the Portworx stand.
Yes.
And let's have one more round of applause for Daniel.
Yes. Thank you.